Now we enter plastic deformation for ductile materials. So as the graph continues to go on, in which we increase the stress applied to this specimen over here, the object will go from the elastic deformation region and enters the plastic deformation region. So plastic deformation sometimes is also called as permanent deformation because the deformation cannot be reversed anymore. If you release the stress, the strain will still be there. Okay, you reduce by a significant amount, but there's still some permanent extension that will happen even if you release the stress and the stress get back to zero. Okay, so stage BC over here, the object deformed beyond its elastic limit. Okay, it's already over the elastic limit, which is point B over here. So now you will start to have plastic deformation or permanent deformation. So what happens, what means by plastic deformation is that the object cannot return to its original length anymore when the stress is being removed. Let's say if you apply stress to the object until you reach this stage already, your stress reach a certain amount already. If you choose to remove the stress, you will still have some kind of permanent extension. Means by even if your stress reach here already, if you choose to release it, then the stress will get back to zero, right? Because you release it means by your force drops to zero, so your stress will drop to zero as well. So if you release it, what happens is, if it's an elastic deformation, if you release it, the strain will get back to zero. Okay, you go follow this path, then your strain will get back to zero. At the end, after you release, the stress get back to zero, your strain should also get back to zero. That's the idea of elastic deformation. But if you have already entered plastic deformation region, even if you release the stress steadily drops to zero, it will not follow back the stress strain curve and goes back to strain equals to zero. That will not happen for plastic deformation. Instead, you follow another path in which once the stress drops back to zero, you'll see that you have a non-zero strain remain after the stress already get back to zero. That means by your non-zero strain here is non-reversible anymore. This stretch over here or this elongation over here is permanent already. So this permanent extension, which we call as OT, is a permanent extension which cannot be reversed anymore. You cannot reduce it shorter than that. That elongation that has happened earlier, it's permanent already. Okay, so but now what I'm trying to highlight here, it's a certain point called C actually. Point C happens somewhere very near point B. Okay, this point C over here, there's a name for this point. It's called the offset U point. Previously in point B, we call point B as a U point of the elastic limit, right? Point C is slightly deviated from point B. That's why I call it as offset U point. Point B is the U point. Point C is somewhere being offset a little bit from the U point. That's why we call it as offset U point. Slightly deviated from the U point. Okay, what kind of definition do we give to offset U point? It's the point where 0.2% plastic deformation occur. What does it mean by 0.2% plastic deformation occur is if you release the stress at this point C, if you release your force, let the stress gets back to zero, you see that there will be a permanent extension which is equivalent to 0.2% of plastic strain. 0.2% of plastic strain means by if you release already, the permanent elongation that happens that cannot be reversed is 0.002% of the original length. Okay, that's what happened if you release the stress at the offset U point. Okay, so this offset U point here is usually a point which people measure as a standard of how strong an object is. Okay, let's say if I tell you this object has 7.2 Pascal for its offset U point. Okay, but this object here has 3.6 Pascal for its offset U point. Then we can know that 7.2 Pascal for its offset U point is a stronger object. Okay, because it can withstand a higher amount of stress without being plastic deformed. Okay, what I'm trying to tell you here is it's a value that people usually use to compare the strength of an object. If an object has a greater offset U point, that means it is a stronger material. If it has a weaker offset U point, a smaller offset U point value, then that means it's a weaker object. That's a value that we usually use to compare the strength of an object. Okay, so in our syllabus, in matriculation syllabus, this point C over here, right, they call it as the U point instead of calling it the offset U point. It's slightly incorrect in my opinion, but actually it's not very significant. Okay, U point is the end of elastic deformation. So at the end of elastic deformation, if you release the stress, technically you will not have any permanent deformation at all, because you have just reached the end. You haven't started the plastic deformation yet. So if you release your stress at the U point, what happens is there will be no plastic deformation at all. But this value is very difficult to measure. Okay, this U strength, this value here is very difficult to measure. So people usually measure something called the offset U point, which they already deform by a little bit. This value is easier to measure, that's why we usually use this value to compare the strength of an object. But our syllabus choose to just mix these two things up, the U point and the offset U point. They just mix it and call it as U point. Okay, but in my opinion, it's slightly incorrect, but I think it's not very significant enough to make an issue out of it. Okay, so yeah, this is what you can take away from here lah. Usually the point that we mentioned in as U point in our matriculation syllabus, that is technically the offset U point. Okay, so let's continue. You continue your permanent deformation until you reach stage D. Okay, so what happens is plastic deformation occurs. The object cannot return to its original length when the force is removed. This is what we have mentioned earlier. If you release the stress or remove the stress, the material will have a permanent extension. It's non-reversible anymore. But once you reach the point D here represents the maximum height of this stress strain curve. Okay, this is the maximum stress that can be achieved for that material. So point D over here, we call it as the ultimate tensile strength. It's the maximum stress that an object can withstand before breaking. After this, you will not see any point in this graph that is higher than point D. That's the highest point that you can find in this graph. So it's the highest stress that can be the maximum stress that the object can withstand before breaking. So we give it a name, call it as ultimate tensile strength. Okay, or the maximum tensile strength. Okay, so going further from here, your material will start to have thinning, okay, in which neck will start to form. Neck is a part of our body which has a significant smaller cross-sectional area compared to other places. Okay, so it's the same idea over here. When we say an object starts to experience necking, what happens is your object starts to have a certain region which has a significantly smaller cross-sectional area than the other places. You get a certain region which is a very small cross-section area. That's the idea of necking. So necking will happens once you already reach the ultimate tensile strength. Okay, so now you can continue to try to do something before it breaks, but what happens is your stress can never go higher than that anymore. So what happens? Permanent deformation continues to occur even after you reach ultimate tensile strength, but because the neckings continue to occur, then this stress will concentrate more at a local cross-sectional area. It will cause the stress experienced by the object to not be uniformly distributed anymore. The stress will be more focused at this region where the necking happens. Okay, so we can continue to say that the pulling force is decreasing because, how should I explain it? Something like chewing gum. Chewing gum, when you stretch it, initially you feel some resistance. But once you experience a thinning in which the chewing gum gets very thin, suddenly it's very easy to pull. Okay, suddenly it's very easy to pull, there's less resistance to it. That's the kind of feeling that I can convey right now. But in this context here, the pulling force will be decreasing. Once you go over the ultimate tensile strength, the pulling force will be decreasing. And we know that stress, okay, stress is equals to force divided by area. Because the pulling force is decreasing, but we always assume our area to be constant. Again, it's not true. It's just that we are assuming it to be constant just to make the calculation easier. It is actually decreasing. There's necking. Okay, it's reduced in the cross-section area. So the area is supposed to decrease, but for the sake of calculating engineering stress, we call it engineering stress actually, we are going to assume this cross-sectional area as being constant. And because we assume it to be constant, therefore the stress will drop together with the force that drops as well. So the pulling force drops, the area constant, so the stress will drop. That's why you see the stress drops from D to E. So that's the idea what happened right now. Necking happens, the stress become concentrated at a certain region. Because of that, your pulling force will decrease. Pulling force decrease by area constant, that's why your stress will decrease as well, such as similar to what you see over here. Okay, then once you reach stage E, you will have reached the end of your journey in which your object will experience fracture. So at this stage, what you can observe is, you can observe that the object breaks into two, and usually breaks at the part where the necking effects happen. Okay, so this is the how fracture looks like. And the stress that is applied during the fracture, the moment where you fracture, the stress that is being applied at that moment is called the fracture strength. Okay, so that's it for the stress strain graph for ductile materials.